Last video, conditioning with densities, observe one variable and the density of the other responds. Slice by slice, this video is about the opposite situation, the one where nothing responds at all. We define independence for continuous variables with a single factoring equation. Watch it cascade down to densities, to conditional slices, and to every pair of events. And then put the definition to work on the unit square, where the two coordinates pass the test, and a third variable, built from the first two, fails it. When does knowing x tell you nothing about y? Chapter 7 answered for discrete variables with a table. Independence meant every cell of the joint PMF was the product of its row margin and its column margin. Continuous variables have no table, but every pair of random variables has a joint CDF. The probability of the quadrant where x stays at or below little x and y stays at or below little y. That is where the definition lives. X and y are independent when the joint CDF factors f of x and y at x and y equals f of x at x times f of y at y. And the equality must hold at every point of the plane. Pick any corner. The probability of its quadrant splits into a product. One quadrant that refuses to split is enough to destroy independence. Because the CDF exists for every random variable, discrete, continuous, or mixed, this one equation is the master definition. The rest of this video is what it becomes once densities enter the picture. Now let the pair be jointly continuous and differentiate. The joint density is the mixed partial derivative of the joint CDF, once in x and once in y. On a factored CDF, each derivative acts on its own factor, the derivative of f of x in x times the derivative of f of y in y. Those are the marginal densities, the joint density factors too. F of x and y at x and y equals f of x at x times f of y at y. Here is the picture to keep. Lay the density of x along the horizontal edge and the density of y along the vertical edge. The joint density over the square is woven from their product. The shade over any point is its column profile times its row profile. The table that factored for discrete variables has become a factoring density. Wherever x is likely and y is likely, the joint is at its darkest. Thin either margin, and its whole row or column thins with it. The two independent Gaussians from when we met the joint density were built exactly this way. There we wrote the product on faith. This equation is the license. Last video made dependence visible, condition on x equals x, and the slice of the joint density at x renormalized becomes the conditional density of y. Slide the observation, and the slice responds. Watch what independence does to that machinery. The conditional density is the joint over the marginal, but the joint is now a product, so the factor f of x at x cancels top and bottom, and what remains is the marginal density of y alone, wherever f of x at x is not 0. Observing x changes nothing about y. Every slice at every x you might observe renormalizes to the same curve. The responsiveness we call dependence has been switched off. This is the discrete lesson that all the table's rows were proportional, now said with densities, and the product climbs back up to events. Take any set S of values for x and any set t for y. The probability that both happen at once is a double integral of the joint density over the rectangle S cross t. Factor the integrand, and the double integral splits into two ordinary ones, the probability that x lands in S times the probability that y lands in t. Independent variables manufacture independent events, every pair of them at once. Exactly the notion Chapter 4 defined one pair at a time. Time to run the test honestly. Pick a point uniformly at random from the unit square and let x and y be its two coordinates. For x and y between 0 and 1, the joint CDF is the area of the corner rectangle, x times y. But x is exactly f of x at x and y is f of y at y. The joint is the product at every such point, and writing the CDF as a product of two indicator integrals extends the check to the whole plane. The coordinates are independent. Now build a third variable from the same two coordinates, w, the sum of x and y. A variable assembled out of x should remember x. Independence needs every point of the plane to factor, so a single failure convicts. Evaluate at the point x equals 1/2, w equals 1, f of w at 1 is 1/2, and f of x at 1/2 is 1/2, so the product is 1/4. The joint CDF is the probability of landing left of 1/2 and below the diagonal line, a trapezoid of area 3/8. 3/8 is not 1/4. X and W are dependent not through anything exotic, but simply because one variable was built from the other. The key idea of this video: independence is a factoring joint. The CDF, the density, and every pair of events split into products, and conditioning learns nothing new. As for the sum W, its distribution is precisely where the next video begins.